Hi, my name is Yunming, and today I'd like to talk to you about our work making graph computations fast, simple, and portable with GraphIt. And this joint work with many collaborators from CMU, MIT, and Adobe Research. If you look closely at the world around you, you'll find that graphs are everywhere. They're powering many important services such as social networks, web search engines, ride-hailing apps, mobile transaction services, and even recommendation engines, right? And achieving high performance is important for these applications because they often have to process graphs with billions of nodes and trillions of edges. At the same time, many of these applications have pretty strict latency guarantees. However, the world of today is really built for dense computations. If you look at the hardware utilization rate of commonly used dense matrix multiply, you can easily get 70 to 90% of the peak performance of CPU and GPUs, right? And then there are a number of optimizations such as prefetch and branch predictions, TLB and cache, or hardware optimizations that are actually built to optimize dense computations. In terms of programming systems, there are a number of abstractions that work well across different domains, such as BLAS for dense linear algebra, Halide for image processing, TensorFlow for deep learning. Right? And we always know optimizations such as tiling, vectorization, unrolling are very effective for dense computations. On the other hand, the world is really not ready for sparse graph computations. If you look at the hardware utilization rate of commonly used kernels such as PageRank and sparse matrix multiply, you'll notice that they can only achieve less than 10% of the peak performance of CPU and GPU. And a large reason of that is due to the fact that the sparse computations usually have cache miss rate that's an order of magnitude higher than dense matrix searches multiply. In terms of programming system, right now, if you want to write a scalable application such as PageRank sparse graphs, working on multi-core machine that's optimized for cache and NUMA, your best bet is still on using OpenMP and Silk APIs that are pretty low level and hard to use.
Right, and to make matters even worse, there's a huge variety in the different type of graphs, algorithm, and hardware. There's a large combination of different types of graph, the different algorithms and hardware platforms. And it's impossible to hand engineer optimized implementations for every combination. And even just the regular library approach often can't actually achieve consistent high performance across all the different combinations. So most of my work is motivated by this low hardware utilization rate for sparse graph computing and the need for a programming system that can handle this variety in data, algorithms, and hardware. So in the first part of the talk, I'll talk about two performance optimization techniques, frequency-based reordering and cache-aware segmenting that was developed to improve hardware utilization rate. And in second and third part of the talk, I'll talk about our work on the GraphIt compiler and domain-specific language that decouples algorithm optimization and hardware for graph applications to achieve consistent high performance. I'll start with the performance optimizations. Right. So we'll use PageRank as an example to demonstrate the bottlenecks of graph computations and kind of pave the way for introducing the new optimizations. So PageRank is an important graph algorithm that ranks the nodes based on their topological structure. And it's very representative of many commonly used graph applications. In the first part of each round of PageRank, you first make a pass through all the edges. You go through every node and you go through its incoming neighbors to accumulate the rank divided by the out degree of the neighbor to the new ranks of the node. In the second part of the loop, you go through all the vertices and multiply the new ranks by damping vector and adds a base score to it. You can swap new ranks and ranks in the end and repeat the process until the rank values of vertices are stabilized. So most of the time is actually spent in the first phase of this processing, where we try to collect the ranks and out degree of the neighbors. So if you simulate the process with, with this small graph with 4 nodes and 7 edges, So it's usually stored as a compressed sparse row data structure where the vertex array stores indices of each vertex into the edge array. And the edge array stores the IDs of the neighbors of each node. Right, and when we try to update the new ranks of each node, it's a sequential access on the node. We just scan through the vertex array. The problem comes when we try to access the rank and out degree of the neighbors as they're irregular or random access. Basically, each node's neighbor can come from any other node in the graph. And if we simulate this access on the ranks value with a cache that holds a single cache line, and we assume that the data of all the vertices, or the rank data, is stored in two separate cache lines. Right. So we start with node 0 that tries to read the data from node 2. So this incurs a compulsory miss to bring the data in. And node 1 tries to read the data from node 0. This is another miss, right? And we just simulate this process as node 2, 3 take turns to read the rank data from their neighbors. Yeah, so what we notice over here is this whole process incurs a pretty high miss rate with 6 misses and 1 hit. Right. So why this is happening, the first obvious reason is that the working set, which is the rank data, is larger than the cache line size. Right. And the second, more subtle but equally important reason is that we often only use part of the cache line. We're reading the cache line contains both node 0 and 1's data, but we often just use read node 0's data. Right? And so the performance bottlenecks that we see in this small example is also true in the larger real-world examples. The working set is usually much larger than the cache size. The real-world graphs often have 10 to 200 times larger data working set than the cache size. And the access pattern is often irregular. You often only use 1/16 to 1/8 of a cache line. And this whole process is hard to benefit from hardware prefetching. A miss to the cache is also oftentimes a miss to TLB and DRAM row, which can cost hundreds of cycles. So if we break down the cycles of PageRank, with the blue part highlighted in blue is the collection phase, and the green part is the second scan. We note up to 80% of the cycles are spent on the collection phase due to the slow irregular memory accesses. Right, so if we actually remove the random access by hard coding everyone to read from node 0, which obviously is incorrect, but this will give us an upper bound or roof line of how much performance we can get if we eliminate random memory access. We know that we can get essentially 2.8 times speed up. Right, and I think what we achieved was with the two techniques I'll describe in the subsequent slides, we'll show you how to get within 2x of having no random memory access. So the first technique I'm going to talk about is called frequency-based vertex reordering. So the key observation that we make over here is that cache lines are often underutilized. Certain vertices are much more likely to be accessed than other vertices. So these are basically popular celebrities in social networks that everyone tries to follow and read. Right, and design is to try to group together all those frequently accessed nodes or vertices in the graph, while at the same time we try to keep the ordering of the average degree nodes to maintain the community data structure. So coming back to this 4-node and 7 edges graph, we first measure the out degree of the nodes and note that nodes 0 and 2 have a higher out degree, 3. That means they are more frequently accessed. And so what we want to do is group together this highly frequently accessed nodes. We achieve this by reorder nodes 1 and 2 and relabel the CSR or graph to represent the changes. This way, we were able to reorganize the nodes data in the memory. And finally, we were able to group together data of frequently accessed nodes into a single cache line. And if we do the same simulation again, we'll note that this time we're getting more cache hits than before, which is much better than 1 hit and 6 misses. Right? And the reason is that by grouping together frequently accessed nodes in the same cache line, we're able to improve the utilization of each cache line. And the second technique that I'll talk about is cache-aware partitioning. The design of this is to partition the graph into subgraphs where the random access are limited to last level cache. And we process each partition subgraph sequentially and merge rank contributions for each partition. Right, so in this example, we partition the edges that are coming out of nodes 0 and 1 into the first subgraph, and the edges coming out of 2 and 3 into the second subgraph. This way, we will able to limit the random access in this first subgraph to just nodes 0 and 1. And if we repeat the simulation, we have to incur compulsory miss to bring in the first cache line for the first subgraph, but all the subsequent reads are cache hits. Similarly, we need one miss to bring in the second cache line, but all the subsequent reads will be cache hits. So this is even better than the frequency-based reordering technique, right? And if we come back to the cycles breakdown that we shown earlier, we show that with reordering, we're able to reduce the number of cycles by 35%. With partitioning, we can reduce it by 50%. And by combining both techniques, we're able to reduce the amount of cycles by 60%. So yeah, so at that point, we were young and we think we solved the problem. We've come up with this great technique that would just impress the whole world and do great cycle reduction for all the applications. But after we got a few applications to work, we soon realized the task of improving graph computation is much harder than we first expected. In fact, when we tried this on the breadth first search, instead of improving the performance, we made it worse by 50%. And a lesson that we learned early in my PhD was that optimizations don't always work across different algorithms and data or graphs, right? And this comes back to the challenge that I talked about earlier in the talk about how there's a large variety in the data, algorithms, and hardware. And so the next part of the talk, I'll talk about how we use the GraphIt compiler to decouple algorithm from optimization to tackle this problem of variety in different algorithm and graphs. So first, we dig a little bit deeper into what type of graphs algorithms that we have, right? So we have this power law degree distributed graph, which has small diameter and poor locality. Examples include basically World Wide Web and social networks. And you got graphs that are bounded degree distribution and with a large diameter, and they usually has pretty good locality as nodes are locally connected. So things like the road networks or engineering meshes. And we've got different type of algorithms. We've got graph algorithms that work on all the edges and vertices. We call them the topology-driven algorithms. Examples include PageRank and collaborative filtering. And we've got data-driven graph algorithms that only work on a subset of vertices and edges at a time. And things like single source shortest path or point-to-point shortest path falls in this category. And we've got different types of hardware, CPU, GPU, and distributed cluster. Okay. On the other hand, we also have a bunch of different performance optimization strategies. You can do a push-based traversal where you can update the states of your neighbors in parallel. In this case, you have incurred overhead with atomics as you could have write-write conflicts, but it traverses no extra edges for data-driven algorithms, so it's pretty work efficient. On the other hand, you can do a pool-based traversal where each node, instead of updating its neighbor, it reads the states from its neighbors and update itself. The advantage of this approach is that you don't need atomics as every node's updating themselves, but you have to traverse extra edges if you're performing a data-driven algorithm. And finally, you can do the partitioning technique that we have described in the first part of the talk that can significantly improve locality, but you do need extra instructions to traverse the two graphs with duplicated nodes. And that was part of the reason why we're 50% slower on breadth first search. So what we soon realized is all of these optimizations are essentially making a trade-off between locality, parallelism, and work efficiency. So if we put the push optimization as a reference point in this trade-off space, then something like a pool-based traversal has better parallelism, but worse work efficiency. The partitioning technique that we covered earlier has significantly improved the locality, but it comes at a cost of parallelism and work efficiency as we're processing one subgraph at a time. And there are many other optimizations that are just points in this trade-off space. So the challenge comes for programmers when they try to develop a high-performance implementation is that they first have to understand what type of graph they're working on, whether it's parallel degree distributed or bounded degree distributed, right? They have to know whether they're working with a topology-driven or a data-driven algorithm. And finally, they have to know some features about the underlying hardware. And for example, if I'm developing PageRank for Google, working on the web graph, which is parallel degree distributed, and it's a topology-driven algorithm running on CPU, then my best combination of optimization strategies might be pool-based traversal, partition the graph, and exploit vertex-level parallelism. But if I'm working on single source shortest paths on the road networks, which is also a data-driven algorithm, then my best combination of optimization might be a push-based traversal with vertex-level parallelism, right? And if I were to run this on the GPUs, we have to exploit edge-level parallelism to saturate a large number of cores. And if we happen to select the bad combination of optimizations, it can be more than 100 times slower than the optimized implementation. So in this part, we introduce this new domain-specific language and compiler called GraphIt for graph applications that try to couple algorithm from optimization strategies. So the algorithm language is part of the language specify what to compute, and the optimization or schedule specifies how to compute it. And with the DSL and compiler, what we achieve is ease of use, improves productivity for data scientists and library developers. And it beats hand-optimized libraries by up to 4.8 times on CPU and GPU, right? And we're working with NVIDIA, University of Washington, and the Swarm team, and many others to develop and improve backends for CPU, GPU, and domain-specific accelerators, right? So I'll first talk about algorithm representation used in the language, and then the optimization representation, and finally, I'll briefly touch on the auto-tuning aspect of things. Right, so the GraphIt language works on vertex and edge sets. For topology-driven algorithms, the programmers can apply a user-defined function on all of the edges in the graph. For data-driven algorithms, the programmer can use a set of filtering operations, such as from, to, source filter, and destination filter, to filter out subset of edges that they want to process, and then apply user-defined functions on the subset of edges. And the programmers can also apply user-defined functions on vertex sets. So coming back to the PageRank example that we have seen earlier, how you would implement it in GraphIt is you first implement how the update edge function that takes as input a source and destination pair and adds the O rank divided by the aldegree of the source and add it to the new rank of the destination node. And then you would define an update vertex function that basically tries to multiply the new rank by a damping vector and adds a base score to it. It swaps the O rank and new rank in the end, as in the original algorithm. In the main function, you iterate for max number of iterations, and you first apply the update edge function on all of the edges, and then you apply the update vertex function on all of the vertices. Next, I'll talk a little bit about optimization representation. So for the scheduling language, we have seen how the algorithm representation of PageRank looks like. And the user can separately specify a bunch of scheduling functions that configures how the algorithm will be executed. So you can use the label S1 in this case to tie back to the S1 specified in between the hashtags in the original algorithm language. And this serves a way of identifying target optimization in the original algorithm specification. And this would generate a push-based traversal based on the code that was specified. It has a two-level nested for loop where the outer for loop goes through all the source vertices, and the inner for loop goes through the outgoing neighbors of each node, and it applies those O rank divided by the out degree of the source nodes and add it to the new rank. And you can further optimize this code by using additional APIs such as configure apply parallelization that would just parallelize the outer for loop And the compiler uses dependence analysis to figure out that there will be write-write conflicts in the inner loop, and we would insert atomic instructions appropriately. You can switch between a push and a pull-based traversal by simply changing a parameter to the configure apply direction API, and this would just interchange the two for loops. So that the outer for loop now goes through the destination vertices, and inner for loop goes through the incoming source neighbors. And the compiler also determines that in this case, no write-write conflicts will happen, so no atomic synchronizations will be needed. You can further apply the partitioning technique that we talked about in the first part of the talk by using the configure apply num segment subgraph API. And this would just introduce another layer of for loop on the outermost level that makes sure we process one subgraph at a time. Here we show the performance of different schedules, where the y-axis is the speed up over the sequential push schedule. And we show that as we find increasingly better combinations of optimization strategies, the performance also increases accordingly. And GraphIt supports many more optimizations than just the ones that I've shown in the short example. There are many different directions, different parallelization strategies. You can configure cache and NUMA optimizations. You can also choose the data layout for vertex set using bit vector or Boolean array. I'll just briefly talk about the scheduling representation. So the compiler takes the algorithm and scheduling functions and generate optimized C++ code. In order to do that, the compiler first have to convert the scheduling functions into an internal schedule representation, and then use it to reason about the composition of optimizations, the validity, and code generation. So we're inspired by the iteration space idea used in the dense traversal, where you can use a vector to represent nested level of for loops. And so here you can use a vector ij to basically represent a two-level nested for loop. Okay. And we're inspired by this idea, and we want to extend this representation to support sparse loops. And to do that, we introduced this idea of graph iteration space, where we extend each dimension in the iteration space vector with tags that can be used to specify the parallelization, partitioning, data layout, and direction of traversal on each dimension. Yeah. Finally, I'll talk a little bit about outer tuner. So yeah, so one obvious issue with this current design is it can be non-trivial for non-experts to find the best schedule. And ideally, the user just need to provide the algorithm and the data, and we'll just generate the best combinations of schedules. And exhaustive search would take a few weeks through all of the possible combinations of optimization strategies. So we rely on an open tuner, which uses an ensemble of methods to basically narrow down the search space so that we can efficiently find a pretty good schedule within 2 hours for even the largest graph. Right, and we even were able to find a few schedules that can outperform hand-tuned ones. So here we show the performance of GraphIt compared to some of the state-of-the-art frameworks. So this is PageRank running on live journal graph, and the number represents the slowdown of of each framework compared to the fastest framework. So a number 1 or a green means it's the fastest of 7, and a red or 8 means it's 8 times slower than the fastest of 7 frameworks. Yeah, so we benchmark not only just for the live journal graph for PageRank, but also for Twitter, WebGraph, Road Network, and Friendster graph. And we not only benchmark for PageRank, but also for breadth first search, connected components, and single source shortest path. So not here, the connected components is using label propagation algorithm, and single source shortest path here is using Bellman-Ford. Yeah, and we compare with state-of-the-art frameworks, and we note that most frameworks are actually pretty good at certain applications and graphs, right? But they're also actually pretty bad at certain applications and graphs. And the reason is that previous work mostly only supported a subset of performance optimizations. Whereas GraphIt were able to achieve consistent high performance because it's able to search through a much larger space of optimizations and use the compiler to generate high-performance implementations. So we were able to even get up to 4.8 times speed up over state-of-the-art by just finding previously unexplored combinations of optimization strategies. At the same time, we were able to reduce the lines of code by an order of magnitude compared to the next fastest framework. So we've seen how we were able to optimize topology-driven, data-driven algorithms, but turns out there are more categories of graph algorithms. The ones that we looked at are basically unordered graph algorithms where active vertices can be processed in parallel in arbitrary order. Right? But there are also an important class of applications that are actually requiring to process active vertices based on their priorities. And the priorities can be changed dynamically. And only vertices of the same priority can be processed in parallel. So in this next part of the talk, I'll talk about how we were able to extend GraphIt to support this important category. And yeah, why you might ask, why is so important to support this ordered category? So it turns out for the few algorithms that does have an ordered algorithm counterpart, few applications that have an ordered algorithm, it can achieve up to 2 to 640 times speed up over their unordered counterparts, even just on this very modest 24-core CPU machine that we have. And to just give you a little bit more intuition as to why this is the case, we use single source shortest path as an example. We'll first walk through an example with Bellman-Ford, which is an unordered algorithm, and then we'll go through delta stepping, which is an ordered algorithm. So in single source shortest path, we're trying to find the shortest path from, in this case, node A, highlighted in blue, to all of the other vertices highlighted in gray at this point. So in this example, the table below shows the shortest distance to each node so far. So in the beginning, it's all infinity except for the starting node A. So in Bellman-Ford, which is an unordered algorithm, each node will update its neighbors to the current shortest distance. So we first update BD, and they will update their neighbors and keep propagating until all the vertices are finalized to the shortest distance. So this took 5 runs and 10 updates using this unordered Bellman-Ford algorithm. So next, if we try to do the delta stepping algorithm, which is an ordered algorithm, and so in this case, we'll process the vertices based on the priority. In this case, that would be the shortest distance so far. So vertex A has the shortest distance first, so A will be processed, and B and D will be updated to 1 and 50. Now B has a lower priority than D, so B will be processed before D, or update C, and C also has a lower priority than D, which is 50, so this way we'll process C first, and then eventually we'll process everything. So compared to the unordered ones, we only need 7 updates, and we're able to save this redundant updates for E, F, and G. So as you can see, the intuition here is all this ordered algorithm, when it's available, it's essentially making a trade-off between parallelism and work efficiency. Yeah, so in this priority-based extensions to GraphIt, we try to decouple algorithm from optimization again for this new category of ordered graph algorithms. So we have to introduce new priority-based algorithm language operators, and we have to figure out what is the optimization space for all this ordered parallelism. And the language and compiler extensions achieve ease of use and consistent high performance. So the first important operator and data structure I'm introducing in the language is the priority queue, where you can use the queue ready set to get the next set of vertices that are ready to be processed. You can always get the current priority. You can use finish and finish node to check whether all of the vertices have been finalized to their final priority, or if a certain node has finished processing. Right? The user can also use update priority min and update priority sum to update the priorities of each node. So how we would use it to implement delta stepping is globally you first declare there's a priority queue, and there will be a priority for each vertex, and the type of the priority would be an integer. In the main body of the loop, we'll construct a new priority queue by saying lower priority I process first, and the priority will be stored in this vector SP, which is shortest path. And in the body of the loop, we have this while loop that keeps checking whether all the vertices have been finalized to their smallest priority. And if not, it would dequeue the next set of vertices that are ready to be processed, which are of the smallest priority. And you can apply this update edge function on all of the edges that's coming out of vertices in the frontier. So in the update edge function, we can use the update priority mean to update the priority of destination nodes to be the minimum of the shortest path to destination node or the shortest path to the source plus weight of the edge. So the key design here is we hide the physical implementation of the priority queue. We never actually pushed or popped. We never pushed explicitly to a priority queue. This way, we're able to basically switch between the different strategies to implement the priority queue for different optimizations and even for different hardware platforms. Right. So again, we've seen the algorithm specification, and like you said, seeing earlier, the scheduling functions can be specified separately to configure performance of the edge traversal in algorithm. And this would generate optimized C++ code. And if you change parameter from lazy to eager, this would generate very different C++ implementations. And I'll introduce what eager and lazy means next. So before we get to that, we have to understand a little bit of how the priority queue is implemented underneath the hood, right? So we're using this idea of bucketing or buckets to implement priority queue, where you would have a bunch of buckets where each bucket contains vertices of the same priority, and the buckets are ordered by their priority. And we insert a global barrier after each bucket to make sure that no priority inversion will be happening. So in the eager mode, we can update the buckets immediately after priority changes. So this is faster when the synchronization is bottleneck. And we can also do a lazy approach where we buffer and reduce all the priority changes before bucket updates. So this is faster when redundant updates are the bottleneck. Right, so to give you some intuition, for applications like K-core, you would actually change the priority, let's say, of a node maybe 5 to 10 times in the same round. In an eager approach, you would have to update the bucket 5 to 10 times, versus in a lazy approach, you can only you can reduce all of the priority changes and update the bucket only once. And we also introduced a second technique called bucket fusion. So one key observation that we make is that oftentimes the buckets of the same priority placed next to each other. And in this case, we can actually remove the barrier, and that would still maintain the priority-based ordering because they're all of the same priority. And this case can happen because when you're processing the first bucket of priority queue, some other node's priority could be dynamically lowered to priority queue, and that gets inserted into the next bucket. This way, we're able to introduce some asynchronous processing in the system without having to break the priority-based ordering. Yeah, and we extended the scheduling space with new APIs to support the lazy, eager, and bucket fusion optimization. You can configure the delta parameter for priority coarsening, and you can configure other things such as when to perform bucket fusion and number of physically realized buckets. And this is all compatible with existing GraphIt API. And here again, we show the same heat map comparing with Julienne and Galois, which are the two state-of-the-art frameworks that actually support ordered parallelism. And we show this for a single source shortest path. In this case, it's actually using delta stepping instead of Bellman-Ford, as we have shown in the earlier heat map. And point-to-point shortest paths, K-core and stack cover. So in this case, we show that we're faster than Julienne, mostly because it supports only lazy bucket update, whereas we support both lazy and eager. And Galois, while it's pretty fast on single source shortest path and point-to-point shortest path, it was unable to support K-core and stack cover because they don't actually maintain a strict priority-based ordering. So it basically relaxed the ordering, which is required for correctness for K-core and stack cover. So again, we were able to achieve consistent high performance on this new class of ordered graph algorithms by basically unifying lazy and eager compute and introduce new bucket fusion optimizations. Next, I'll talk a little bit about our recent work on trying to incorporate different hardware backends for graph applications. So you might ask, why does hardware incorporating different hardware backends important? If one is pretty fast, then we can just use that one platform always, right? So it turns out basically the features of different hardware determine that there is no one winner for across all the different hardware platforms. So for example, take GPU and CPU, which are the two most popular platforms for doing graph computations these days. GPU has this amazing memory bandwidth, up to 900 gigabytes per second. I think it's even more these days. Tremendous amount of compute power. But its memory size is pretty limited. And the cores are not as powerful, right? And CPUs, you've got this large cache size per core, and you can get up to 3 terabytes of DRAM these days. And you get more powerful cores with out-of-order execution that can hide a lot of the long latency of irregular memory accesses. So because of this difference in features, stuff like GPU are good for throughput-oriented algorithms with abundant parallelisms, so like PageRank and connected components, running on graphs that can be actually like stored in the limited amount of memory, right? And CPU is good for latency-sensitive applications with limited parallelism, so like single-source shortest path down road networks, or just simply graphs that doesn't feed in the memory of GPUs. And to make the space even more diverse, these days we're seeing the advancement of a lot of domain-specific accelerators for sparse computing, such as the Swarm architecture developed here at MIT, Symphony by NVIDIA, Hammerblade, University of Washington, and many more through both industry and academia, right? And all of this hardware really need domain-specific transformations to be able to fully take advantage of features such as hardware-accelerated speculative execution. So because of this emergence of this diverse hardware platforms, it was critical to get a reusable compiler infrastructure for graph computing that we can reuse the hardware-independent analysis and optimizations. And to do that, we have to separate out hardware-independent and hardware-specific optimizations. And we have to support new hardware platforms easily. So we have to make sure that we can modularize the changes to compiler so that we don't have to rewrite the compiler every time we try to add a new hardware backend, right? So we use GPU as an example in this short piece of the talk, and we show that for GPUs, for example, they still need to do hardware-independent optimizations, such as direction optimization, parallelization, and just maintain priority process ordering for ordered algorithms. And at the same time, you want to take advantage of the GPU cache, avoid GPU kernel launch overhead with kernel fusion optimizations, and exploit the features on GPUs to achieve good load balance. So previously, the GraphIt only worked for CPU, and now we're introducing this design of using the GraphIR, which is a domain-specific intermediate representation for graph computations, and the GraphVM, which is kind of the backend that runs the GraphIR. So this way, with the GraphIR and GraphVM framework, we're trying to achieve high performance and portability across different platforms. So for the GraphIR, the key idea is we want to be able to use the meat end of the compiler to do hardware-independent analysis and optimizations, and use this IR as a common interface across the different backends or graph VMs. So the GraphIR would incorporate two main components: the arguments, which captures algorithmic information, and there's a metadata that captures hardware-independent optimizations. It is also flexible enough that can be extended to support hardware-specific optimizations in the GraphIR. Next, I'll talk a little bit about the GraphVM or virtual machine. So the idea of GraphVM is we want to be able to take as input the GraphIR and perform hardware-specific compiler process to further optimize it and generate implementation code for the hardware platform. At the same time, we also incorporate optimized runtime libraries for each individual hardware platform. And this way, we can produce an executable that's fast and efficient for this particular hardware platform. And again, we use GPU as an example to demonstrate our work. And here, UGF is a GraphIt extension, and we show that we're able to achieve consistent high performance over state-of-the-art frameworks such as Gunrock, G-Switch, and SepGraph. And again, this is largely due to the fact that by decoupling algorithm and optimization, we're able to just search through a larger space of optimizations. And with this GraphIR and GraphVM design, we're just working on the ability to easily incorporate new hardware platforms. So yeah, there's a lot of work in the space of graph computing, as Simon has mentioned in the first part of the talk. So yeah, so there are a lot of DSLs that actually try to separate algorithm from schedules these days. This work is obviously inspired by the Halide work. And so in this work, we just focus on how to apply the same methodology or idea in this graph compute and sparse computing space, right? What does it mean to have a scheduling space in sparse computations, right? The challenges are very different. There's also obviously a large number of graph frameworks, optimizations, and architectures that support both unordered and ordered parallelism. So in this work, we focus on this narrow space of cache optimizations. But more importantly, we focus on how to actually just compose together all the different optimizations into one package that the user can easily use to explore this large space of existing and new optimizations. And finally, there are a number of domain-specific languages for graph computations. And the main difference is we just focus a lot on just how to search through the space of optimizations. In the process, we'll learn a few lessons. No set of optimization fit all the graph applications well. You really have to select the best algorithm and optimization strategy for each hardware platform, and you need software optimizations to take full advantage of the underlying hardware. So we start with this challenge of hardware utilization and programming system on sparse graph computations, and we're able to significantly reduce the cache miss rates and improve peak utilization rate for PageRank and a few other applications using the new optimization techniques that we have proposed. And we were able to replace the low-level C++ programming API with this high-level GraphIt language to achieve ease of use and high performance across different algorithms and data structures. And we're trying to get it to work on more hardware platforms. And again, everything's open source. Welcome to try it out on the graphitland.org. Yeah, it's a lot of work, and I don't take credit for everything, obviously. There's a lot of people who have advised us on this project, and many students who have worked on various components contributed very significantly, such as Ajay, Vlad, Lexman, and everyone. I have the honor to work with many of brilliant master and undergrad students in my years, and I'm really grateful for that. Yeah, and I want to also just thank the MIT Graduate Christian Fellowship, obviously the commit group for those discussions and all the fun stuff we had, and thank my friends at MIT and elsewhere, and thank my parents-in-law, and obviously my wife, Meng Chen, for supporting me through all these years. Yeah, with that, I'll conclude my talk and open up for questions. Thanks.
Okay, so let's open up for questions. If you have questions, just please raise the hand. If there's no deluge of questions, I guess you can just go unmute yourself and ask the question. I guess probably unmute yourself and ask the questions. I don't think, I thought there'd be hundreds of questions coming in, but it doesn't look like it, but yeah.
Hi, Yunming. So I was wondering if you can talk about some of the challenges for making this work for dynamic graphs.
Yeah. So it's a great question. I think, I think we're getting a lot of requests to work on how to support busy graphs, dynamic graphs where graphs are updating and changes. So I think a large part of it is just maybe providing new APIs for the users to say what happens when the graph has changed. In the large part, they have to be able to say if they're processing some nodes and the nodes are deleted or removed, there has to be some default action if a certain node doesn't exist anymore. So in that end, we probably have to change the API or extend it to provide basically more user-defined functions to do it. And I think, so yeah, so basically one important part is how to be as transparent as possible for the user in terms of working under a dynamic graph. If we could actually automatically derive possible actions from the static specification, that would be pretty great as well. And I think the other is just how to make sure that we can get good performance when the graph is changing, given that a lot of optimizations that we worked on assume the graph is static. So like partitioning the graph assumes that the graph will remain the same largely. And as a result, if the graph is dynamically changing, some schedules or optimizations might not make sense. And we have to figure out what are the schedules that does make sense, similar to what we did for the ordered graph algorithm, and possibly extend the space of optimizations to support dynamic graphs.
Great.
Okay,
Arvind has
thanks.
questions. Arvind has a question. Arvind, you can go next.
Did you call me out, someone?
Yes, yes.
Okay. So, hi, Yunming. Wonderful talk. To what extent the tuning depends on the size of the data, size of the graph itself?
Yeah. So I think it's actually oftentimes I think it's a non-linear function in terms of size of the graph. Mostly the size it makes a difference when this number of vertices or the working set of data that you're accessing is larger than the last level cache size oftentimes, because then the average memory access latency can go up by an order of magnitude when it has to fetch it from DRAM. So for example, if the graph data largely fits in the last level cache, then the size doesn't matter that much. But when it does go outside of the cache, then it matters a lot. But if it doesn't feed in the cache anyways, then it doesn't matter if it's too large or very large.
Sure.
Yeah, but I think at the same time, it also depends on kind of the structure of the graph. So for example, in a lot of our experience, we work on some web graph, which is pretty big. But what we found surprisingly is that actually the locality is pretty good. It's actually almost as good as like a road network. And the reason is just because the degree distribution is very concentrated on a small number of popular websites. So in that sense, the size was not a great predictor in terms of the performance bottlenecks that we're seeing. On the other hand, social network, that's a big issue.
So most of the results you have presented today, these graphs did fit in the last level cache, or they didn't?
Yeah, it's a great question. I think for the social networks, most of them has at least like 40 million vertices, so they usually don't fit in the last level cache. For the road networks, they're usually smaller just because there are less number of nodes, roads than people, and they usually fit in pretty well in the last level cache.
And do you have a feeling for what is most common these days when people are trying graph algorithms in practice? How big a data set do they use?
Yeah. It's a $1 million question, I think, that everybody's trying to ask. We've been in all these meetings. Yeah, so I think from the limited experience I had with some of our industry contacts, I think this can range quite a bit. So some people work on relatively small graphs, and some folks actually try to work on pretty large graphs that doesn't fit in like a single machine. Some of the contacts we have, they have also graphs usually doesn't quite exist as a standalone data structure. They're often kind of coexisting with other database systems. So the graph might not be too big, but it might be hard to fit them in one machine. Yeah, so I think these days for popular algorithms, from the couple meetings that I attend, I think community detection seems to be pretty important. And there's a lot of interest in getting graph neural networks to run fast. And obviously subgraph isomorphism and pattern matching stuff is always a pretty important application.
Thank you.
No, thank you. Yeah.
I had another question. It was a bit building off of what Julian described. So I'm trying to reason about graphic scope. So, Julian mentioned or, inquired about how you might support, dynamic graphs or streaming computations. And, what else doesn't fit into the GraphIt framework right now, but does fit, broadly as a graph computation? What are the limits?
Yeah. That's a good question. So I think there are a couple areas that we're actually thinking about extending the language a lot of times to. So obviously graph computation is a very diverse field, and we're nowhere near covering, let's say 80% of all the possible graph algorithms. I think, like Julian's mentioned, dynamic graphs is definitely very important. And there are many algorithms that, for example, are using more complicated data structure for stuff like clustering. So that kind of stuff we don't yet have a good grasp. There's stuff where we try to merge vertices into a larger vertex, and that require modifications to the graph, and we don't yet have a good grasp on that. And obviously, like the newer categories that I was mentioning to Arvin just now, the community detections and graph neural networks, they require kind of like a combination of graph native operators, but also possibly like a lot of linear algebra stuff. So how to figure out going back and forth between different abstractions is also kind of important. So yeah, that's my quick take. I'm sure there are a gazillion number of new applications that we don't quite support, and we're adding new operators even as we speak right now. We have students working on adding new features.
Okay, thank you.
There was some hands up. I can't see who was. Okay, go for it. You can just go for it. Unmute yourself and ask.
Hi, Yunming. Thanks for a great talk. So I'm also very interested in a similar line of work. So I'm just wondering how did the GraphIt project started? And when you started, did you try to look at a subset problem first, or do you try to generalize the paradigms to make it available for more algorithms?
I think that's a very good question. In the beginning, we started out very naively. This is old days, me and Salman. We're just optimizing PageRank for another project. We're not even starting to work on the graphs at that point. We're just trying to optimize PageRank. So basically, we got all this optimized code from Intel, and we're like, oh, let's study how to do them. And we realized, especially this was back in the old days with Vlad, and we came up with some good optimizations that we got good performance, and everybody was exciting. This is a very competitive field, and somehow we thought we got an edge. So we rolled up a paper, and we tried to get more optimization, more applications to work with the optimizations that I described in the first part. And it turned out to be not an easy task that we thought we would be. So we started out trying to optimize just PageRank collaborative filtering, although kind of topology-driven algorithms, and then we realized those optimizations that we come up, while pretty effective for the subset, doesn't generalize that well. And then we use performance counters and really deep into all these other applications and try to figure out what's going on, and realize that the performance bottlenecks of all these other algorithms are pretty different from PageRank. So they require a different strategy in terms of optimizing it. And that kind of, motivated us to build, since we also built Halide, and we thought it was a great idea to apply this idea of decoupling algorithm from schedule optimizations to be able to try out the different optimization strategies at the same time without having to hurt the programmability of the system. And that's how the GraphIt project got started. And this way we're able to basically incorporate more and more optimizations and new optimizations and achieve some portability as well. Don't know if that fully answers the question, but that's kind of a 2-minute breakdown of how things got started.
I see. Yes, it does. Thanks. Yeah, it makes sense. Let's talk more offline.
Yeah, thanks.
Okay. Any other questions? There should be more questions. Of course, there will be questions in the closed session, but it would be good to have other questions.
Hey, Saman. Yeah,
hi.
okay.
Hi, Vivek.
Hi. Yeah, how are you? So, boy, Yunming, good job. The years have flown since you left Rice 6 years ago. I just a slight anecdote, as Yunming will remember, the second year undergrad, his first research project was to parallelize SSCA on graphs a long time ago. But so Yunming, one thing I'd welcome your opinion on. The number of computer architecture people are proposing accelerators, for near memory processing, in-memory processing, sparse matrix accelerators. In these new proposals, which directions do you think might be most promising for the kind graph algorithms that you target with GraphIt? Yeah, so I think your input there will be very helpful.
Yeah, yeah, definitely. Thanks for coming, Vivek, and thanks for all the help in undergrad and master years. Yeah, I still remember working on between centrality in my second year, and actually, I have a master student who's still working on the same topic of trying to get multiple starting points to work even today.
This is thing for everybody. What you start doing research as an undergrad, keep following you through your entire career. You can't give it up.
Yeah. So I just want to get that off first. Really grateful for all the help in the first 5 years, and so I don't pretend to be an expert in computer architecture. So I'll just give my personal opinion in the space, since I did read quite a few papers in that space. I think, yeah, there are a lot of different proposals, and they look equally interesting, right? A lot of times, like you mentioned, there are works that try to move some of the processing logic to the memory side, so as to avoid this whole DRAM traffic. And I think there are many exciting work here at MIT that try to leverage cache coherence and all this other stuff to make sure that random access is fast. I think I feel like they each have their own trade-offs, and they might be good for different types of graph applications. Since the space, like I mentioned in talk, is pretty big and it's a lot of variety, it would be hard to say one direction would be most promising for all the graph computations. So I think I can give a few examples. I think, for example, something like PageRank or sparse matrix vector, where the computation is pretty simple, right? It's just multiply, add, and stuff. So if we can move that kind of compute logic to the memory side, and that could save a lot of memory costs, I think that's an obvious idea that's going to be pretty good. But obviously, the downside is many of the more complicated algorithms where the processing logic doesn't feed in the space of a simple multiply and add. You have querying global data structure and maintaining priority ordering. So for those stuff, I think doing it on the memory side, it would not be as effective. And there's some applications, as mentioned, they don't even miss the cache that much. So moving the processing logic to the memory side probably won't help as much. I think, but it's going to be very useful for those really large graph processing like PageRank, as I mentioned. And then there's the other stuff that tries to, for example, the Swarm one, a speculative execution at MIT. I think it's a pretty great idea. It can hide the latency and exploit parallelism for priority-based algorithms by just able to execute, basically in our case, it's multiple buckets. So that can actually get a lot more parallelism than just doing like a CPU kind of architecture. But I guess the downside here is if there's no priority-based ordering needed in the algorithm, then it might not be as effective. So I think generally, I feel like many of this domain-specific architecture would be good for a subclass of graph algorithms, depending on kind of the bottleneck of the computation. And I think to some extent why we're supporting multiple architecture is because we want to be able to have the user just write once, and even being able to just not auto-tune your optimization strategy, but even auto-tune your different backends, right? So depending on the graph and algorithm specification that was specified, you can potentially even select the best domain-specific accelerator for your particular use case. Yeah, that's kind of my take on this very complicated space.
Thank you.
Thanks Vivek for coming. Okay, other questions?